Hello. So I'm going to be talking you through how the BBC, well, I'll give you an introduction to the Semantic Web first, and give you like a bit of context of the BBC and how they've used it in the past and how we're sort of using it now. So I'll just go straight into it, or not. Yep. So BBC started in 1922 with radio, went on to broadcast TV in 1936, then sort of you get the BBC Micro in 1982. Anyone here ever used a BBC Micro or would have one? Wow, I knew there'd be some of you. I don't really know what they are because I'm basically 12. So going on throughout the sort of innovations we've made, it brings us to today. So why have I told you that? Because it's quite significant and kind of explains the problem we're having today, in that the legacy of our innovation has allowed to keep us ahead of the game, but it's also we've got a lot of legacy systems in play, and they're all kind of existing in their own separate data silos. So bringing in the concept of a data silo, it's a metaphor for some data on a system which is difficult to access from another system or from other parts of the organization. And they can form for various reasons, cultural or technological. I think the BBC is both, just the way it's formed and the size of the organization. And that kind of sets the context for the problem that we're dealing with. We want to bring all this data together to get sort of actionable insight from it all. But that's not a unique problem. Plenty of other companies face that problem. What makes us unique is that we're public service. We're a public service broadcaster. This comes with the caveat that we're funded by you, hopefully, your loyal license payers. And we exist to serve the audience, whilst remaining impartial and non-commercial. And that kind of sets up an interesting problem space for us, because we have to consider ethics. We have to consider what's right for the audience. So we raise our sort of questions while we're working on this stuff, like, do we just serve audiences content which they know and love and they can just binge on it all day? Or do we actually challenge their views? Do we take them out of their kind of chamber of things at the risk of potentially making them value the BBC less? It's an interesting question to pose. How much data do we collect? What are audiences comfortable with? I imagine most people would say no data, but then how are we supposed to serve them if we don't know? So there's a balance, and we have to do it delicately and ethically enough to, again, provide for the audience. And then do we open our algorithms up to public scrutiny? There's not a lot of companies really go down and open source their algorithms and things, and we'd like to do that, but then there's risk of people gamifying the algorithms and things if it's news recommendation or something like that. So with all these questions as context, this is the kind of things we're thinking about while developing these new systems. So I'll just briefly introduce you to myself. I'm 23, data engineer at BBC. I started my interest in data science and data engineering in my third year project. We got told to upload the human brain, theoretical project. Turned out it's impossible unless you have £50 billion and know a lot of smart people. That was kind of my first dip into big data and data science. Then into my fourth year project, which was detecting dangerous mosquitoes using smartphone audio sensors. It turned out to be pretty effective. It was really amazing stuff and really got me hooked. Where I went straight out of uni into a startup for a few months called Q, and we were working on a pair of smart glasses to help visually impaired people pick up non-verbal communications by translating visual stuff into sounds. That was excellent, and now I find myself here talking to you lot as a data engineer. So our team, Data Lab, we're fairly new, a year old. We've been tasked to solve this problem of these data silos, connect the BBC together. We exist within connected data, within technology, strategy and architecture, within design and engineering, within the BBC. Okay, crack on with the semantic web. I'll start with the context. Before the internet, maybe some of you were around, I certainly wasn't. In academia especially, there's papers were referencing other papers, and to go from one paper to another, you actually had to get a physical copy of that. You had to do. It was sometimes done by post. It was generally a difficult process. So this bloke came along. Who knows who he is? Anyone? Just shout it out. Yes, I'm glad. I would have been very upset if no one knew. He came along and proposed HTML, HTTP, and URLs as a kind of system to abstract this process away and make it easy to connect documents together. He proposed the actual idea of the semantic web in the late 90s, published it in 2002 in the Scientific American. But first we'll show the sort of early versions of the web. So Web 1.0, this was known as the read phase of the web. So websites are mostly static documents, but you could click from one website to another without knowing anything about how they're all connected. It abstracted away this process, and he's there in the middle of it all, just doing it all. And then, oh yeah, I forgot to bring that up. That's what it looked like. It's beautiful, as you can see. I wish we could go back to that, but that was pulled from the Wayback Machine, the BBC website, in 1996. Yeah. And then we go to Web 2.0, the kind of right phase of the web. This is kind of where we're at now, where active participation, sharing, collaboration from users is encouraged, but kind of funneled into different silos. So Facebook, LinkedIn, Twitter, all these other ones, they all collect users' data and keep it to themselves, and that's where the value proposition comes from, holding this data. And this doesn't, well, okay, going on to Web 3.0, the idea of it, the semantic web, the execute, was that we'd share all our data. These application silos wouldn't exist. Everyone would just have this common data to use. But that's not a realistic kind of thing to assume. It's not likely to happen. This is where their value comes from. They're not just going to suddenly give away all their data. And for that reason, there's very mixed opinions surrounding the semantic web. I'd personally say that the original vision of the semantic web will probably not happen. There won't be this open spread internet. Everything's accessible, all the data's accessible. But it turns out the technologies behind it are very useful for the problem that we're trying to solve, linking data across silos. Because you can link data of different types and really emphasize the relationships in this data. So linked data is what Tim Berners-Lee called the semantic web done right. It's kind of like an implementation of it. It has a few key concepts around it. Everything has a URI. This is a uniform resource identifier. You might catch me saying other things, but it's definitely that one. Everything has a URI. France has a URI. PyData has a URI. And I know that man's beard there probably has a URI, if you're modeling that. And they're all distinct. They must be ideally dereferenceable, so have HTTP URLs, and you follow one and you get more information on that, and you can traverse the whole sort of system of URIs. You must define the relationship. You can't just throw in a load of objects and expect them to link up and talk to each other. Well, without some machine learning, but that's kind of later evolution of this. And ideally use a standard format, so your data can be shared. You can push public Sparkle endpoints, push public endpoints where you can query your data and public and other companies can access it. So I'll take you through the technology stack of the semantic web, starting with RDF. So RDF is a data model for representing resources and relationships between those resources. It's flexible and schemaless, so it relies as a descriptive schema rather than a prescriptive schema. So as opposed to relational databases, they have a prescriptive schema, which if you try and add data which doesn't fit with the schema, it's not going to be happy with it. It's not going to work. It's quite resistant to change. Whereas if you add data to this descriptive schema system, which fits the schema fine, if it doesn't fit, then you can still do it and it can still link in. It adds information. It's not necessary. It's quite a simple way of representing the knowledge, but it's so powerful, and the fact that it's machine readable makes it so much more valuable. You can have machines understand all the facts and statements you're asserting and make new inferences from those facts, which I'll talk about later. So the form of RDF is you've got subject, predicate, and object. So the subject could be something like sky, the predicate could be colour, and the colour object could be blue. So another example, I work at the BBC. BBC produces Doctor Who, and Doctor Who has a rating of excellent. And these are all assertions of facts, remember that. And there's many different serializations of this RDF model. These are just ways of representing it. RDF is the model, and not to be confused with turtle and quads and triples, etc. They're just different ways of explaining the same model. So we'll go on to ontologies now, which form quite a fundamental part of the semantic web. Ontologies allow us to represent knowledge as a series of concepts linked together. It's a way of managing knowledge, and it could be very, through rules and constraints, and it can be very easily extended. So if you've got a data set or a triple store with loads of data in, and you want to add more of a different form, you can extend the ontology, just keep it growing. And using that, you can infer new knowledge, which I'll talk about on the next slide. As an example of some existing ontologies, we have RDFS, RDF schema, which is the kind of most basic. You can start inferring, you can start saying classes and properties and things about these RDF statements you're making. It's kind of the most basic one. Then extending from that, we've got the web ontology language, which you can start making. It's a lot more complex than RDFS, and you can build upon that and use that for inferences, which is quite powerful, but you've got to be careful with it, so I'll talk about that later. And then we have kind of other existing ontologies, which are domain-specific knowledge. So the simple knowledge organization system used to link organization systems together, or the friend of a friend, FOF, where it talks about human relationships, social networks, contact information, things like that. So there's lots of domain-specific knowledge. And then, as an example, a very basic example of an ontology, say I was linking two BBC systems together. One was TV system, one was radio, and they're described as video and audio in their separate systems. In this system I'm bringing them into, I can say they're both a subclass of media, and then through queries and things I can say I want all the media items, and it'll give me anything which is a subclass of media. And that's a very basic example, but it just shows you kind of how these relationships are defined. We can take that one step further and start to use inference. So if we say Gerald is a cat, and then we can say this cat is a subclass of the animal. If we run an OWL reasoning engine over this, we can actually infer new information from it. So we can create this triple without actually adding it in, saying Gerald is an animal. And you can do much more advanced things than that. It's a very basic example to illustrate a point. And next we have Sparkle, which is the query language, and I thought it'd be much better to illustrate it through a demo rather than just talking through the syntax. So we'll set out the context of it. We'll be using dbpedia, which is a sort of public-facing Sparkle endpoint of lots of collected media from different Wikimedia projects. So it's got a load of information about different subjects, basically. And we'll be accessing it using rdflib, which is a Python library, the most common one to access and manipulate RDF, and Sparkle wrapper, which wraps around the public endpoint and sort of abstracts it to your Python code. So let's pose this question. I'm going to read it out because it's difficult to remember. Let's find the genres of any music produced by a band with a member born the year that Elon Musk was born, where any of the members were also born in the UK. Okay. And, it might be on a different screen, actually. Oh, it's there. Excellent. I think okay, I'm kind of see. Okay. Yeah, I'll put it on presentation mode. Can you all see that? Is that okay? Yeah. Get my glasses. So we start by creating a object to interact with the Sparkle endpoint. So the and I'm going to be using PyCharm's sort of handy shortcuts a lot. I just put these up here handily for me. This is the DBpedia endpoint that anyone can access. You can play along at home if you want. I'll do it here. Pop it in here. Just import that. And then we have our store object, so let's build a query. We'll start with the most basic query, where we basically get all the triples from the database. So if we start with select, probably all familiar with select, subject, predicate, and object, which is the things I was referencing before. Then we need a little where in there. And anything inside a where is basically, to put it simply, pattern matching. So if I say the pattern is, then that's basically saying I've got 3 variables here without any constraints, match all the triples. And then we'll execute that query by just going store.query and pop our query in here. Yes, and I've just made a little handy function here to print out the results. So let's run that. Hopefully won't need to. Oh no. You can never trust a live demo, can you? Well, I do have one I made earlier, but it would be nice to show you this. Any input? That should take... Oh, I know exactly why. Because... No, that's a lie. Okay, well, I'll go to the one I made earlier and just talk you through that. It's a shame. Can I change project from here? I'm going to have to exit demo mode. Sorry about this, folks. I'll call it Plan B. Okay, so I'll just talk you through this. Basically, same, slightly different syntax here, but that, So we've got the Sparkle store here. That's what I did. I imported the module instead of the... I can go back. Too late to go back now. I'm invested in this now. Okay. So we've opened our store with the endpoint here. And then we've created a namespace manager object, which is part of RDF-lib. That needs an RDF-lib graph object to operate on, so we just pop our store, like a Sparkle wrapper store into that. The graph takes that and treats it as a sort of native inbuilt graph object, and then the namespace manager is a way of managing these ontologies that you want to use to query. So I added DBR and DBO, so that describes the DBpedia resources, which are objects, things like Elon Musk or a band, anything like that. And DBO, which is the ontology, so the things that describe the relationship between these objects, and the FOF, which is friend of a friend. I would have used that earlier in the demo, but it's too late now. So I'll take you through. Here we've just bound the namespaces using the namespace manager. So now if I send a query, these abbreviations here will expand to these URLs by the time it hits the endpoint. So what we've done here is we've selected the genre from all the way down here, said distinct because we don't want a load of repeated genres, because that was our final goal, to get the genre, which blah, 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 blah. And we've said find the birth year of Elon Musk and call it this variable here, Elon Musk birth year. We then sort of, that will match any triples which match that, and there will only be one because he only has one birthday, unless, well, he might have two. So separately, we find any bands. So this pattern here will just find everything which is tagged as a band in DBpedia. We then take that, using this shortcut here, we're still operating on this band variable, and we say we want band members associated with this band, and then this slash here we'll traverse to the next link, and we say we want the birth years of those band members. And we have this variable here, Elon birth year, which we've already kind of defined. So it'll match all the triples with the bands who have band members who have the same birth year as Elon Musk. Much in a similar way, we'll do the band members again, get the birthplace, which will be a town, and then we have to get the country of that town, so we've traversed 2 links there, and we can say in the United Kingdom. And of this band that we've now narrowed down to these 2 kind of criteria, find the genre. So let's run that, and it will run. Yeah, and we got one result, and fortunately it's very boring. It's a cover band. Probably the most disappointing answer, but there you go. We've managed to do quite a complex query live. And yeah, so I close the presentation now. No, it's still there. And so we've kind of found some triples which match this graph. 1 triple, in fact. So that was kind of the linked data stack. We got the RDF as the data model, ontologies to link these entities together, add new information, and we have Sparkle to query this data that we have. So what is it like altogether? You get, potentially if you do it right, you can get a knowledge graph. So this basically sits on top of all of your data silos, abstracts it away, and makes your data an actionable asset. You can see, you can get insights like the silos weren't even there. So I'll just go on to show you what's available at the moment. There's a ton of different graph database solutions, all quite different. So some of them have particular implementations of the stack. Some can import and export it, but they work with something else. And some are kind of a different model, like a property graph model, where you can describe the relationships. I'll talk about that in a bit. Yeah. So there is limitations with the linked data stack. It's a high learning curve, because this idea was born out of academia sort of 20 years ago, and its main development has been through academia. And I found when I was researching this stuff, trying to learn it, if I went beyond the basic stuff, sort of Googling how to do X, Y, Z with Sparkle, it's just academic papers and the occasional poor sod who's trying to ask on Stack Exchange and getting no answers. Because of this kind of difficult uptake, there's also a limited availability of tools. If no one's using it, no one really wants to develop for it. But there is hope. There is starting to be an uptake from the big providers. So AWS are releasing Neptune. It's in preview at the moment. This is a massively distributed graph database based on some of these technologies, but also you can use some others. So it's quite versatile, quite interesting. And another trouble with this is the documentation. It's all very correct and accurate, and perfect if you know anything about it and how to use it. But if you're learning it, it's just takes time, and people don't want to do that. People are lazy. So then next limitation is binary statements. RDF you can say anything in a triple, but you can't say anything about that triple. If you want to add provenance information, such as if I was tagging a piece of media with a tag, how confident am I about that tag? You have to then add, have to reify the data, add another, 3 or 4 triples to represent that one thing. It's a bit messy, and the more you do that, the sort of further away you get from your sort of core data model. But it is possible. It just requires a bit more thinking about. But because of that, if you've got a pretty complex data set which requires lots of provenance information, then you get a sort of proliferation of triples. You can end up sort of compared to a property graph, which you can label the connections, you can end up with a database 10 times bigger. Then we have the open world assumption. So I was talking about inference before, and the OWL reasoning engines are used to do that. But it uses a open world assumption. So if I say Gerald is a cat and cats eat food, but I then add a triple saying Gerald is food, OWL would not say, nope, this is wrong, Gerald can't be food, he's a cat. I would say cat is food, and eat is. It would try and make something consistent, even if it didn't make sense in your model. So you've got to be careful for that. There is tools at the moment, such as Stardog, which does have integrity verification. But it's just something you've got to be aware of when you're working with lots of L reasoning. And then we have the question of, is it scalable? That's kind of the most common thing asked about RDF and the semantic web stack. And usually when dealing with scalability in a sort of traditional databases, you take your data, split it up, put it on different systems, scale it out horizontally, and usually the data clustered on these systems is related. And this is a bit more difficult with RDF because the unit of data is much smaller and these relationships can become a lot more complex. So the difficulty to partition increases. It becomes like a graph partitioning problem, which is difficult. It's not impossible, it's just a lot more challenging, and it's less established as a sort of scalable platform, so there's still some work to be done. But saying that, there is hybrid solutions which do exist, such as JNS Graph is built on Google Bigtable-like databases, so Cassandra, things like that. And you can have that as your data storage, and then have the layer of RDF and other semantic technologies on top of that. So there's some limitations there to be aware of, and you know, it's not something you can just choose and it'll solve all your problems. It fits in certain contexts. So to give it a context with other data storage paradigms, you have a key value store, very basic, often used for caches, just keys and values. The values are sort of opaque blobs in regards to the query engine. Then we have the next level up for that, which is the document store, similar to key value store, but the value is now indexable. The query engine uses it to optimize the queries. But it's not really built for relationships. You can have some relationships, but it's not designed for that. But they're both blazingly fast and simple. And then we have wide column databases, which is what JNS Graph is based off. You have massive amounts of data. It's hugely scalable, very denormalized, so lots of duplicated data, but you can just scale it out like that. And then you're probably familiar with SQL, most of you. It's a very mature technology. Got a large choice of tools that's been around for ages. But if you start trying to shove new types of data into it, it'll struggle, especially if you've got a huge established system. To change a column can be a $1 million problem. You know, all of this entirely depends on your context and choosing the right storage solution. So then, bringing the graph databases, I briefly mentioned earlier property graphs. So with property graphs, you can label the relationships. So if I'm saying how confident I am about a tag, I can just pop that on. The property itself is an object which you can attach things to. With these systems, there's not really a standard for them, an open standard, so each solution tends to work with a different language. Some of them have sort of things bolted on where you can use Sparkle and import and export RDF, but it gets kind of messy, and it wouldn't be the same as if you hand designed it for a sort of RDF-based system. Although, saying that, if you do want that kind of thing, want to close it off, then it's excellent fast transactional support, and you've got strong path analysis. Then we have RDF databases. There's a standard data model. This is all sort of defined in W3C standards. Sparkle RDF and ontologies are all defined there, open standards, and there's a lot of platforms built upon this. Because of this, your data is highly portable. There's no vendor lock-in. You could be using 3 different systems simultaneously, although that would defeat the point of trying to unify everything, but if you wanted to. And you can use the sort of powerful inference tools of OWL and the things I was discussing before. So you've got to choose a thing appropriate to the problem, and we at the BBC have tended to stick with RDF because we're about opening up, we're about sharing our data where we can, providing services for the audience. So I'll just briefly take you through the linked data and how they use it in the BBC. So there's the linked data platform. It was big in around 2012. Some of you may have heard of it. They aggregated content that matters to the BBC and its audiences. So things outside of the BBC and then some things within the BBC. They put it into a knowledge graph and popped it all together. They used it to power the World Cup 2010 and the Olympics 2012. So it's kind of perfect for that solution where you have these entities of athletes, teams, countries, events, all linking together with different kind of medals and amount of people playing in the game, different countries, etc. It's quite powerful. And when you can start doing those complicated queries, you can really get quick insights without any extra cost of hiring someone to delve through it. And today, I believe it's still in use to serve the topics for the BBC News app and serve some BBC sports website content. And it's using some journalistic tools where if a journalist is writing an article, we'll have our tag generating API. It'll generate tags on the fly and then put these into the links data platform, which is now BBC Things or Connections. Not really sure what it's called anymore. And then recommend articles as they're writing so they can see what's already existing on the BBC and they can get a real context of what they're writing about. And then we have the research and education space, and their idea was to, it was a 4-year project, and they collaborated with lots of academic students, curators, to aggregate content from libraries, museums, galleries, broadcasters, put it into one space. So students and teachers, academics, curators, they can all use this to gain further insight and sort of base their research on this. And then we have how our team are using it at the moment. So we have been given this problem of data silos, and we're working on a content graph to solve it. It's quite exciting, it's quite difficult. I joined 6 months ago, and I've learned a huge amount. I actually sort of was exposed to these technologies 6 months ago, so I've been learning and working with them and come to understand a lot of their shortcomings, but a lot of the power, and we really think we can write something amazing with this, and possibly even a hybrid solution. It doesn't all have to depend on this graph. So this will power recommendations for a new app we're releasing. Those are a team working alongside us. And on the other side of it, it'll provide a platform for the rest of the BBC to use. So we'll be exposing our knowledge to the rest of the organisation and exposing it out so the audiences can make use of it. And we're hiring. So if any of you are interested in working on a problem like this, get in touch, come talk to me after, whatever you want. We've got 4 roles: lead data scientist, lead data engineer, architect, executive project manager. Shoot us an email, talk to me, whatever you want if you're interested. That's it. If you have any questions.
Hi, thanks for the talk. I kind of get the query side of things, but I don't get the indexing side of things, because with the silos, they're not going to be in any kind of typical state that you're going to want to go and index from. So how does that side work?
So I think you're talking about the ingest process of how you get the data from. So ideally, you'd have to, if you had a system which was constantly bringing in data, you'd have to first do an initial ingest of that data and convert it into RDF. So that requires some kind of modeling, some process. And then you take that in, and then you can set up a script to monitor that and bring in change notifications and things.
So you have to do that yourself?
Yeah.
Thank you.
Else?
Thank you for the talk. You mentioned that you're building the content ontology. How does it happen with the new programs as they come out? Will there be special people employed to just populate it in your database?
Sorry, could you repeat that?
Like when a new program comes out,
yeah.
For example, somebody has to input it into this new database that you are building.
So when a new program comes out in the BBC, it's put into the PIPS database.
Mm-hmm.
That stores all the program metadata. And then we will set up, after doing our initial ingest, as I was talking about to this gentleman, we will subscribe to change notifications from an Amazon SNS topic, and that will we can just fire an update to the graph store.
And there's no manual steps there. You can just ingest it raw.
Well, yeah, we'll have to go through a conversion script to model it in RDF, but that's just a matter of squishing it up into a different shape.
Well, that's great. Yeah, usually there's a lot of effort that goes into maintaining the RDF normally.
Yeah, so we're building it first connecting to PIPS, building like quite generic systems. So we'll start with ingesting this video clips metadata, then we'll extend it to other systems. And because RDF and the ontology are extendable, it absolutely presents itself to this kind of situation.
Thank you.
No worries.
Do we have any? Yes, we do have more questions.
Yeah, so do you know of any other commercial, like Google Knowledge Graph or even IMDb using RDF? You know, it's still quite academic, right? You don't see any. You know, why do you think it didn't take off? So why do you think it's different now?
I think it's different now because big companies.
Yeah, so you know, if you look at the most of the IMDb or Facebook or Google Knowledge Graph, you know, they don't expose a RDF or a interface, right?
They won't, you say?
They don't, right?
Yeah,
currently?
they don't. Yeah.
So currently, the only RDF or Spark QL interfaces are for academic projects or open source ones.
Yeah. So was what I was kind of saying about the kind of vision, the original vision of the semantic web didn't really work because no one wants to open up their endpoints like that. But I think it does. The technologies are still valid for doing it within an organization. So you don't necessarily have to open it up, but ideally you would. So I don't know, things might shift with the way people value data. Things might change. I don't know.
And then how do you envisage ontologies will be synchronized across organizations? So you had this bands thing, right? So everyone who has a bands database, like Spotify and things, would need the same schemas for bands and things.
So with OWL and RDF, you can create your own ontologies. So if Spotify calls it a band and Apple Music calls it a musical group, you can just, in your sort of connecting ontology, if you're ingesting it, say musical group is the same as band, and immediately that will treat them as the same thing. No worries.
Okay, thank you. So we probably have a time for one more quick question. Any more questions? Okay, that's it. Oh.
Yeah, thanks. Just following on that one, I don't know if you have, for example, come across a schema.org, which is, the Google version of RDF, and that's kind of taking over just because, well, every website wants to be captured by Google. So I've got more take on, but I don't know. I still think, RDF is better. But have you considered, for example, a schema.org?
I don't know a huge amount about that. Is it compatible with the sort of linked data stack, or are they trying to build it as a separate system, which is?
Yeah, it's essentially the way, if you're a web developer developing your website and want to be gathered and, pass all this, the idea of the semantic web by Google to be part of their knowledge graph, then they would recommend you just follow the schema.org standard.
Okay.
And that kind of, there are ways to transfer and translate into RDF Lights, because there are several versions of RDF. But that seems to be the one that is taking more, just because of the need of people to be, found by search by Google.
So that will probably take off and raise awareness of it, but there'll still definitely be a need to run your own sort of in-house knowledge graphs and things distributed on AWS or something. So I think they'll probably develop side by side with positive effect, I imagine.
Okay. Theo, fantastic talk. Let's thank Theo.
Thank you. Thanks.